Dear viewers, welcome to Vijnan Saraswati channel. Today we'll see in this video we'll discuss about when a transverse wave is transmitted through two different wires of different impedances. At the boundary of these two media or these wire strings, what happens, how the wave behaves, that means how much part of wave is transmitted and how much part is reflected, and their coefficients will see the reflective amplitude coefficient and transmitted amplitude coefficient. Okay, so that depends on the material what we take, that is the impedance, their impedance. So reflection and transmission or reflection of transverse wave at boundary of two strings of different materials. This is the thing we are going to discuss now. So let us take a string of something like a string of impedance Z1 and its linear density mu1. Say here whatever the propagation constant we take is k, and it is connected to another string, and it has impedance Z2 and linear density mu2. The wave propagation constant is k2. Here the boundary between these two strings is this is the boundary, okay, at x is equal to 0, something like. So when these two strings are stretched with the same tension, when a wave is made to propagate along this, then the incident wave reaches to this boundary point, and there part of the wave is reflected back, part of the wave is transmitted into the second medium. Okay, so how much part is reflected, whether the incident wave reflects completely back, comes completely back, and whether how the phase changes, all these things we can based on two equations we can say how that wave behaves. Okay, so let us see in this region 1, say this is region 1, this is region 2. In region 1 we will write equation for wave equation for incident wave. So wave equation of incident wave yi is equal to, it has some amplitude a1, so some incident wave you take, it has amplitude a1 sin omega t minus k1x. Similarly, in the same region, some part of wave may be reflected back. Okay, so some part, depending on the value of Z2, some part of the wave is reflected back with different phases. Okay, so that reflected wave equation is, say it is reflected back with amplitude a2, or let us take incident amplitude ai and reflected amplitude ar sin omega t, because it is reflected back, k1x plus k1x. Okay, so in the same manner we'll write in region 2. In region 2 only transmitted wave is there. Okay, so transmitted wave is yt is equal to the amplitude of the transmitted wave at sin omega t minus k2x. Okay, so again About the boundary, if you see, about this boundary, some boundary, let us take B, about B, that is about boundary B, the incident wave, sum of incident wave and reflected wave, their combination is should be equal to the wave transmitted. Let us substitute all these equations here. If you by substituting these wave equations, plus a or sine omega t minus plus k1x is equal to yt is at sine omega t minus k2x. Let us apply at B. We have considered x is 0 at boundary, x is 0, that if you implement over here, if you substitute x is 0 in this equation, we get a1 sine omega t, k1x is 0, plus ar sine omega t, k1x is 0, is equal to at sine omega t. We can cancel sine omega t both sides. Now we get a1 plus ar is equal to 80, equation 4. So here we got the relation between this incident wave amplitude, reflected wave amplitude and transmitted wave amplitude. About that boundary, let us write force components. Okay. So when you write force components about that boundary, the what is the force component over here? The force component is T into dou y by dou x. This is the force component. So in region 1, the force components are T into dou y by dou incident wave, dou by dou x of incident wave plus dou by dou x of reflected wave, and this should be equal to T into dou yt by dou x. So these are the force components, and about that boundary, these force components sum of value should be same in the both sides. Okay. So let us differentiate this equation 1 and also equation 2 and also equation 3. Will substitute over here. So we get, see here, T into differentiation of equation 1 with respect to x gives the sign differentiation is cos theta, internal differentiation we get minus k1. So minus k1 into ai cos omega t minus kx we can write, minus a1 ai into k1 cos omega t minus k1x, and differentiation of, here I took just t common, differentiation of equation 2 with respect to x gives plus ar k1 cos omega t plus k1x, and this is equal to how much? T into differentiation of equation 3 with respect to x. Again there internal differentiation minus k we get, minus k2. So I am writing that here itself, minus at into k2 cos omega t minus k2x. Okay, this is the thing we get. Now let us apply condition x is equal to 0 again here. When you apply the condition x is equal to 0, t minus ai k1 cos omega t plus t ar k1 cos omega t is equal to minus t a2 at k2 cos omega t. See in the equation, the both sides we can cancel omega t. Okay, when you cancel omega t both sides, we get here minus AI tk1 plus AR tk1 is equal to minus AT tk2. Take this tk1, but t into k we know impedance into omega, z omega. So that will substitute here, minus AI t into k1 is z1 omega plus AR, this is z1 omega again, this is equal to minus AT z2 omega. Okay, omega also we can cancel both sides. Now we have minus, if you take common, AI z1, and z1 also will take common, AI minus AR into z1 is equal to minus AT into z2. Minus also we can cancel. So here we got AI minus AR into z1 is equal to AT into z2. This is equation 5. So here we got a relation that comprises of amplitudes and impedances. So this, using equation 4 and equation 5, let us do some mathematics over here and substituting. See, from here let us substitute this AT value in the equation 5. Substituting equation 4, that is AT value from equation 4 in equation 5. So AI z1 minus AR z1 is equal to AT is AI plus AR. So AI z2 plus AR z2, just I multiplied it. Now we will take AI and AR common, and if you write this side AI, if you take common, z1 minus z2, this is equal to, if you take AR common, this is z1 plus z2. Okay, so AR by AI is z1 minus z2 by z1 plus z2. This is one of the important parameter of in deciding the material, in choosing the material for different engineering purposes. So this AR by AI is reflection amplitude coefficient. Okay, so in the similar manner we'll find out AT by AI. So from this equation, from equation 4, so AR is AT minus AI, will substituting this in equation 5, that is in this equation. So AR has to be get substituted over there. AI minus AR is AT minus AI into Z1 is equal to AT Z2. Okay, so here AI Z1 minus AT Z1 minus of minus plus AI Z1 is equal to AT Z2. Okay, so AI Z1 plus AI Z1 is 2 AI Z1 minus AT Z1 is equal to AT Z2, and we'll take A to that side. AT AI Z1 is equal to, if you take AT common over here, it is Z1 plus Z2. So AT by AI is how much? AT by AI is 2 Z1 by Z1 plus Z2, and this is another important equation in deciding the material. So, see the equation AR by AI, this is again transmission amplitude coefficient. This ratio is called transmission amplitude coefficient. Okay. Now, let us discuss few cases over here. If Z2 is infinite, so Z2 is infinite means what? This part whatever here at the boundary, this part 1, that is string 1, is connected to a rigid support. Impedance is infinite means it is connected to a rigid support. If Z2 is infinite, how will be these ratios? We'll see. So when Z2 is infinite, AR by AI is Z1 minus Z2. So here we get negative value, and divided by Z1 plus Z2, here infinite. So overall overall minus infinite by infinite we can think of. That is, if Z2 is infinite, AR by AI we get negative value. That means what? AR is equal to minus AI, negative 1 we can think, negative 1 we can write. So AR is equal to minus AI. What is AR? AR is amplitude of the reflected wave, AI is amplitude of incident wave, right? So AR is equal to minus AI in the sense what? The with same amplitude, but it is reflected back. The complete wave is reflected back instead of transmission. Instead of going into second region, it is completely reflected back. Okay. Now another case we'll see, case 2. In case 2, Z2 is greater than Z1. When Z2 is greater than Z1, see here you will get negative value. That means what? AR is equal to AR by AI is some negative value you will get here, but it is not equal to minus 1. And see this equation here also, if you substitute Z2 is greater than that is denominator becomes higher, so this value becomes little lower. So finally AT by AI value also is there. So see this previous case, if Z2 is infinite, something by infinite here will get, something by infinite is 0. That means what? AT by AI is 0, that point also will mention over here. From that equation, here let me write over here, from that equation, in this case AT by AI is becoming 0. That means what? AT is equal to 0. AT is 0 in the sense there is no amplitude is 0 in the sense there is no wave in the second region when the impedance is infinite. Second material impedance is infinite, no wave will be propagated into it, no wave will be transmitted, the total incident wave is reflected back. So we got AR equal to minus A. Magnitude if you take same. Okay. So in the second case, when Z2 is greater than Z1, here some negative value is there, that is AR equal to some minus of some value into some P, let me write AI, some value is there, and AT by AI cannot become 0. AT by AI has some value, it cannot become 0, means some wave is transmitted, some part of wave is reflected back, but reflecting back with phase change. If incident wave is this, so reflected wave has some phase change. So in that manner we can draw it. So it is reflecting with change of phase. let us take another case. Z2 is Z2 is less than Z1. What happens, we'll see. Now this case, when Z2 is less than Z1, this value will be positive. Okay, so AR by AI is some positive value, some value number is there, right? So AR is equal to, from here, AR is equal to some P into AI, some number is there, number we get. Now see this equation, if Z2 is less than Z1, okay, here also it gives some another value, that is AT by AI also cannot become 0. AT by AI also, somewhere let me write over here, AT by AI also cannot become 0. That means what? AR by AI ratio is positive. Positive in the sense, part of wave is transmitted, of course, because it is not 0. Part of wave is reflected back, but these two are in phase. Initially, in this case, when you get negative, it is out of phase. Both the waves, incident wave and reflected wave, are out of phase. In this case, when impedance of second string is less than the first string, then the reflected wave and incident wave are in phase. So this is the information we get from this, and using these few important parameters of these materials we can deduce, right? So if you have any doubts, you can write in comment section. Those questions will be answered, and share among your friends. We'll see another topic in next video.